Okay, well, welcome to the Installer Plaza, sponsored by our good friends at Valent. We're going to session now, which is going to cover seasonal performance factor and heat pumps, why it matters. We're going to hear how SPF offers a more accurate view of heat pump efficiency than COP and SCOP. We're going to discover how to include SPF in system design, improve performance, and better inform customers. And to guide us through, I'm delighted to welcome technical design engineer at Rinnai, Sean Elan. Now, we're going to do this in a different style. Sean is going to present from over here. We've got some images on the screen, which will also be shown on the big screen. And he's going to talk to you and talk you through some slides with some fascinating information on that he's going to guide you through. So I might as well hand over to you, Sean, and let you take it away.
Yeah, is this working okay?
It's
Can you hear
working.
me fine? Okay, yeah. As he mentioned, I'm Sean Elan. I'm the lead technical design engineer at Rinnai UK. And today I'm going to be going through a presentation that I've put together regarding seasonal performance factor for heat pump systems. And we're specifically going to be looking at domestic hot water applications. It's here to provide kind of a different performance measurement to SCOP that we see in the industry. So yeah, let's get into it. So the industry predominantly uses two forms of performance measurements, being COP and SCOP. COP being your coefficient of performance and SCOP being your seasonal coefficient of performance. Delving into them into a little bit more detail, COP is your heat pump's efficiency at an instantaneous point in time. So that'll be at a specific external ambient temperature and at a specific flow temperature. You'll have your heat pump will be associated with a specific efficiency. So at -7, flow temperature 50, it could be 3, while at 7 degrees that'll change. And that's why seasonal coefficient of performance is also used within the heat pump industry because it gives an average of these COPs over a full heating season. There's some problems with relying on SCOP for domestic hot water applications. Again, if you're looking at a lot of heat pump manufacturers' technical bulletins, when you look at SCOP, it's usually at flow temperatures around 35, 45 degrees, while for domestic hot water applications, we more use temperatures 55, 60, 65 degrees. So as you increase that flow temperature, your efficiency of your heat pump drops. And when we're designing heat pump systems within the domestic hot water market, we want to be able to provide that transparency for our customers to show kind of what efficiency they're getting. Another problem is heat pump manufacturers kind of test their heat pumps to get the best out of them, while when they're installed across the UK, it might not be to best practices, should we say. So you're likely there's gonna be some discrepancy between the SCOP value that you've seen and what you'd actually get once you install the system. And then finally, SCOP also only considers the efficiency of the heat pump. It doesn't actually go into anything else that's within the system. So if you've got a hybrid system, for example, it's not taking into account any energy used by the backup heater. And kind of all that leads to a lack of system congruity. So the system that you've been designed is going to perform to a slightly lower standard than what you're expecting, which we don't want, and that's why we believe seasonal performance factor should be the efficiency measurement used for heat pump systems. So seasonal performance factor evaluates a system by calculating the total amount of heat outputted divided by the total amount of electricity being inputted over a full heating season. So slightly similar to SCOP, but instead of just focusing on the heat pump, which is one cog of the system, we're looking at the entire system. So it's accounting for high heat losses in the building circuit, which is recovered by backup heaters. It's accounting for accurate temperature profiles. So SCOP will be based on a German temperature profile, while when we calculate SPF, we put in the exact coordinates of where it's going to be installed and have a specific weather data set that we can import into our model to be able to give accurate efficiencies of the heat pump throughout the year. And it also accounts for any energy-intensive ancillaries in the secondary circuit, such as your backup heater, your pumps, storage losses, etc. And kind of the goal from our side is to be able to provide actual representation of what your system's going to be performing like, so you're not let down once you've actually installed it. And this kind of goes along with your operating cost and your carbon production, which we'll go through when we go through the case study. So kind of our goal is firstly to be able to provide the industry with a more accurate performance efficiency when we're looking at heat pump systems rather than SCOP, and also actually standardise the methodology for domestic hot water systems, so people understand kind of what their system's going to perform to prior to installation, rather than it being installed and then you're kind of let down with what has been installed because you're assuming to get these high SCOP values, which sometimes aren't the case, especially for domestic hot water systems. The methodology has been taken from a report called the SEPAMO report, which has got a long-winded name, so it's been kind of shortened down, but it introduces 4 different equations, being SPF H1, SPF H2, SPF H3 and SPF H4, where each one of them takes more and more of the system into account. I'm gonna, because this presentation is a little bit shorter than what I would usually do, I'm just gonna showcase SPF H2 and SPF H4 because they're kind of the key ones to show the main benefit of SPF when we're looking at hybrid systems. I'm also not going to account for any space heating within the case study because it's to show the benefit of domestic hot water systems. However, SPF can be used for space heating. So, yeah, if that's of interest to anyone, I'm happy to discuss that side of it after the presentation. So, SPF H2 evaluates the performance of the heat pump as well as the equipment to make use of the source energy available. And kind of what that means is it's the efficiency of your monoblock heat pump. So it's the electricity being inputted into your compressor and the electricity being inputted into your fan, which is blowing ambient air over your evaporator, and you also account for your heat being outputted by the heat pump. It's worth making the comparison now that SPF H2 is similar to SCOP. However, the 2 main differences between SPF H2 and SCOP is that SCOP is based on a German temperature profile and it's based on a flow temperature of 35-45 degrees, while SPF H2 is based on the accurate location of where the heat pump's being installed, and it's based on an accurate flow temperature to give a more realistic representation of what efficiency your heat pump's running at. Moving on to SPF H4, this is kind of your system efficiency. So it's calculating all the heat being outputted by your system divided by all the electricity being inputted. So you would have, as you say, your heat being outputted by your heat pump, heat being outputted by your backup heater, divided by your electricity into your heat pump, into your pumps, your backup heater, as well as any pumps on your secondary circuit. Pretty much anything that you can provide us with details that either output heat or require electricity, we can account for that within our study to make it as real life as possible, should we say. So now we've introduced the equations, how does it actually work as part of the case study? I'm going to be running through calculating the SPF for a student's accommodation based upon that SPF H2 and SPF H4. Kind of the 2 systems we're going to be comparing is a 100% heat pump system using high temperature R290 heat pumps, and also a hybrid electric system. So your heat pump is sized at 40% and then your electric cylinder is sized at 60%, which is topping up the pre-fed water from your heat pump and also keeping your system at temperature. To be able to actually calculate an SPF study, we need to input an average hourly ambient temperature profile. So this particular case study is being based off Glasgow. So we would have a weather data set based on Glasgow, which we can import to give the efficiency of the heat pump throughout the year, as well as average hourly domestic hot water profile. So for this specific student's accommodation, we're assuming every single day throughout the year, they would have this much hot water being required hour by hour. This has been based on literature regarding how much hot water student accommodations use, as well as past case studies to showcase for this particular size hotel kind of what your peak demand would be, which is at around 8 AM being 4,000 litres. Just to give a little bit more detail about each of the systems, so your 100% heat pump system is comprised of 750 kilowatt R290 heat pumps, which have a flow temperature of 60 degrees. They feed into a 2,500 litre thermal store for minimum water content purposes, and then that heat is split over 3 2,000 litre cylinders. The key thing from this is the flow temperatures being at 60 degrees. While for our system 2, our hybrid system. We're using R32 heat pumps, which don't go as high as our high temperature. You're normally capped at about 55, but the specific flow temperature for this system is 50 degrees. That 50-degree water is then pre-fed into our electric cylinders, which top it up to 60 degrees and keep the system at temperature. Some of the assumptions, again, we've gone through the first two about the ambient temperature profile and the hour-by-hour domestic hot water profile, but we've also just assumed linear extrapolation between outdoor temperature test points. Heat loss in the secondary circuit's been assumed for archetype buildings and kept the same for both systems. The storage loss has been based on spec data for the cylinders rather than the actual installation location, because it could differ slightly. And then just static heating conditions, so based on technical information rather than if there was any wind, rain or humidity. And then immersion coil efficiency is assumed to be 100% for this study. So moving on to the results, there's kind of three key ones. The first one is that the most obvious one, should I say, in your winter months, being your January, February, November and December, both your SPF H2 and SPF H4 are lower than in your summer months, and that's pretty self-explanatory in terms of it's colder externally in your winter months, and therefore your compressor needs to work harder, therefore more electricity needs to be inputted to get to the required flow temperature, and your efficiency is lower in your winter months. The two more important kind of outputs from this result is firstly looking at your SPF H2 for both systems, your system 1 being your 100% heat pump system and your system 2 being your hybrid system. We can see that your system 1 has an SPF H2 of 2.63, while your system 2 is 2.96. So again, if you was just given this piece of information, you may think, why wouldn't I go with system 2? It's heat pumps running at a higher efficiency. It's likely going to be cheaper because it's got a reduced amount of heat pumps and more electric cylinders. But when you actually look at your SPF H4, you can see that your system 1 only drops by 0.12, while your system 2 drops by about half. The reason for that is because if we go back to them two schematics, our system 2 hybrid system's only running at 50 degrees, while our system 1's running at 60. So the heat pumps run at a higher efficiency when its flow temperature is less, while for our system 1, it drops slightly because our compressor needs to work a little bit harder to get up to that higher temperature. When you actually go to SPF H4, which is your actual entire system efficiency, you can see it only drops by a small amount for your system 1 because you're taking into account your pump being used, your storage loss, any ancillaries on the circuit. While for your system 2, it drops by half because now we're including your electric cylinder efficiency and how much that's being used. So again, graphically, we can kind of see our system 1, our SPF H2 is always going to be higher because it's the most efficient technology within the system, while our SPF H4 drops off slightly. However, it still kind of follows the same curve. While if we look at our hybrid system, the drop-off is far greater, and that's because your electric cylinder usage. So the more your electric cylinders being used, the more it's pulling that blue line closer and closer to a 1, because your electric cylinder SPF is pretty much 1 throughout the year. It doesn't change with ambient temperature profiles. So kind of the point I'm trying to make is we can design your system to whatever SPF you require, depending on your initial kind of constraints and goals. If you want your electric immersions only to be used 10% of the time, 20% of the time, your SPF H4 is going to be far greater and closer to that SPF H2 line. While if you want a hybrid system which is using electric cylinders 80% of the time, it's going to pull that line closer and closer down to 1. So just to extend this further from an operating cost point of view, again, we said that system 2 might look more beneficial looking at SPF H2, which we associated to be similar to SCOP. But if you look over a 10-year forecast, the operating cost for a heat pump only system is 36% less than it would be for a hybrid system, because more electricities need to be sourced from the national grid, meaning it's going to cost more, and that kind of is similar for your carbon production. As more electricity needs to be sourced for your hybrid system, more carbon's going to be produced. So we kind of want to work with our clients to be able to, based on if they want to reduce carbon, if they want to reduce operating cost, if they just want a cheaper system which is as efficient as it could be based on what the budget is, you can work with us to be able to design an SPF model for you to give you a visual of all these specific metrics that could be important to you. So yeah, just to conclude, we believe more information should be supplied at the design stage, because that's going to improve your system congruity. If we understand your system more, we're going to be able to make a more accurate SPF model, which is going to give you a visual of, as you say, all these metrics that we said: energy consumption, operating cost, carbon production. We also think less reliance should be on SCOP when you're looking to try and understand system performance. If you want to just understand which heat pump works at a higher efficiency based on a generic kind of circumstance, as you say, they all work off a German temperature profile based on a 45-degree flow, that's fine. But if you want to understand what your system's running at and how efficient your system is, then you should be looking at SPF. We also want to standardize SPF methodology where you specify a system boundary, because as you've seen, if we give an SPF of H4 and someone give an SPF of H2, you could have very different metrics. So it's actually educating on understanding what these different boundaries are and kind of what the end user wants to see. Usually an end user would want to see their entire system performance based on everything, because they're more concerned with the operating cost and carbon production. Also, awareness of SPF and the effect backup heaters have, which we kind of showcase with the case study. And finally, we just believe that a decision shouldn't purely be made on CapEx. It should be made on CapEx, OpEx, carbon production, seasonal performance factor, as well as SCOP and COP. So you've got all the information to make the best decision for you. And that's something that we at Rinnai can supply. So yeah, I guess if anyone does have any projects that this sounds interesting for, we can have a chat after this, and yeah, I can design a model for you. But that's the end of my presentation. Thank you, yeah.
Well done, and thank you. And I know you've raced through that compared to how you normally do it. But I just thank you for that presentation, Sean. Does anybody have any questions or comments they'd like to make at all? You've got yes, let me come to you with a microphone, sir. And you can tell us your interest, why you're here. And
Hi, my name's Joe Moran. I'm Director of Building Services for Carter Synergy. We're a local company, but national, and we manufacture in refrigeration cabinets and cold stores around the world. I met Rinnai about a year ago, and I've worked with the guys since. We have a facility only a few miles away from here, and it's completely run on a solar thermal air source heat pump hybrid skid. We use it as a demonstration model because a lot of our end user customers challenge us not only as a service company, but they expect us to be assisting them in delivering game-changing technology to work across their entire portfolio. So customers such as DHL, Centre Parks, a number of commercial operations come to us for cutting edge or leading technology. Everyone knows that an air source heat pump is potentially the way to go. What I like about Rinnai is they work across the entire system. So we've got a pipeline of business that we feel is being pulled through, and it wouldn't have happened without some of the assistance we've had from Rinnai.
basically, you're a walking advocate for Rinnai. I mean, amazing. They couldn't ask any better. Anybody else want to make a comment or a question they got to ask? Well done, sir. Look, I just want to ask you, if SPF is sort of more holistic than SCOP and better than SCOP, then why isn't the industry currently adopting this as such as standard, so to speak?
No, completely. Again, from our perspective, SCOP kind of has to be used by heat pump manufacturers because they usually only supply the heat pump. So they want to be able to understand what the efficiency of their heat pump is against all others in the market. I guess the differentiator with SPF from a Rinnai point of view is we supply the entire system. So we've got all the kind of spec sheets and technical data for the entire system, so we have the ability to calculate and model the SPF. I think it should become a requirement more so in the industry because people are more concerned with how their system performs rather than how their heat pump performs. And I think if people knew SPF was available and was out there, they'd be a lot more inclined to go down that route rather than just understanding what their SCOP is.
So it is useful for the domestic market.
Yeah, SPF can be applied to any kind of system from a space heating point of view, a domestic hot water system point of view, as well as any archetype building. We usually operate largely in the commercial space. However, we also design a lot of heat pump systems for domestic properties, and SPF's actually been used majority in the domestic market. The government has a paper out there where they calculate the SPF of, I think it's over 300 space heating systems for a range of archetype domestic buildings, and the goal, I guess, from their side and how I see it, is they want to gather enough data so they can set limits for what the SPF of domestic buildings should be, especially for new builds coming in, because, as you say, SCOP is not always, it's a generic efficiency measurement rather than an accurate efficiency measurement for a lot of cases.
Brilliant. You're going to be hanging around if anybody else has got any more questions.
Yeah,
I'm
of course.
guessing. I want to say, great presentation. You're clearly passionate about it because you know your stuff, and that's really impressive. Now, you come from Liverpool, I'm guessing. I'm no detective, but
Yeah.
are you red or blue?
I'm a red.
A red. And when they said SCOP, did you mishear them, or was it it's been a great season for them, though, hasn't it?
Yeah, it hasn't been. It's been good.
Not
It's
bad.
Better next year.
Brilliant. Well, look, congratulations, John. Thank you very much for your presentation. And you're still around, as I say, if anybody wants to ask you any questions. Give it up. He's done a great job.
Thank you.
Very much.